Hello, George Romanic here. Today we are investigating a problem that has very special place in the history of physics, and that's Foucault pendulum. Foucault pendulum can be used to demonstrate that Earth is rotating. What is this device? Well, in the absence of any better pendulum, I'll use my necklace as a very, very poor pendulum indeed. So, Foucault pendulum would be the following. Let's assume that this pendulum is very, very long, 50, 60, 100 meters long. 100 meters long string, and there is a mass at the bottom of this pendulum. Now, this would be equilibrium position for any pendulum, including that one. And now we displace that pendulum, it will oscillate, just like so. Now, if the experiment is carefully performed, and indeed this is very long pendulum, then if we displace it for a very small displacement angle, and let's say we displace it like so, and let's call this x direction, doesn't matter. Let's call this x direction. When I displace it in the x direction, it will oscillate, but if it is oscillating for a very long time, it will be affected by Earth's rotation and Coriolis force. And eventually, Coriolis force, if we are in the northern hemisphere, will deflect motion to the right, and from the initial x direction, the pendulum will start oscillating in the y direction, and then go back to the x direction and so on. Of course, I'm doing it here with my arm, but naturally, the change from the zonal direction to the meridional direction would be due to the rotation of the Earth. Another very important thing to note here is that the initial displacement has to be very small, namely, the angle has to be small. If we make angle very large, then all kinds of nonlinear effects will dominate the problem, and we will not be able to isolate the effects of Earth's rotation. So to recap this demonstration, very poor demonstration, is to say that if we have and you will see why the pendulum needs to be very long when we start with mathematics. If we have very long pendulum and we design experiment carefully and we displace it, the motion will be affected by the Coriolis force. So now let's investigate this problem mathematically. Just give me a second. Okay. So, what we have is, let's say, a ceiling, and you can see the text of the problem now on your screen. If we have this ceiling and the pendulum is hanging down, there is a mass attached to the end of mass m attached to the end of the string. String is basically massless. There is no friction, we assume, here at the hinge point, and the length of this string is L. This is equilibrium position for the pendulum, and now we displace it for some angle theta. Now, this angle theta needs to be small, but in order to make this visible, I make it large, okay? So, if we displace this, of course, pendulum will swing back past the equilibrium point, swing here, and eventually be affected by the Coriolis force. So let's say that here we have coordinate system, that this is x direction, into the page is y, and up is z. I hope you can see these. Displacement is r. Okay? This vector r means how much we displace this pendulum from the equilibrium. Now let me make this schematic one more time, because in the next schematic, we will investigate forces that are acting on this pendulum. So again, we have pendulum that is now displaced from the equilibrium position for the angle theta, and theta is small. And small means sufficiently small so that cosine of theta is approximately 1 and sine of theta is approximately theta. This comes from Taylor series approximation, and you should know that this video is a little bit more advanced than some of the previous videos, but that's how it goes. It's going to become even more advanced when we end up with with a system of differential equations that is relatively nasty. But on this channel, by now, you should know that we celebrate relatively nasty systems of differential equations. So that's a beauty. At any rate, going back here, this angle theta needs to be sufficiently small so that these are reasonably good approximations. Given that, now, if we accept that, what are the forces? Well, let me maybe take some colors a little bit. Why not? The forces, there is gravity, mg, acting down. And notice there will be tension, T, on this string. Because this mass is attached to the string, it doesn't fly off. So that means it has to be tension, force that is keeping it attached to the string. And there has to be another force that we are investigating actually here, and that's Coriolis force. Now, if we say that velocity is, well, in this case, it will be in this direction. So I purposely don't want to put vector. You will see why. So this would be velocity of this mass. Then Coriolis force would act to the right of this vector in the northern hemisphere, and I assume we are in the northern hemisphere. So Coriolis force would be into the page like so. Now the reason I didn't want to put this velocity vector over here, because now I would like to decompose this tension into two components. Horizontal component of the tension and vertical component of this tension force. You see, if I put this over here, then it would be messy. Now, you need to recognize if this is angle theta, then this is also angle theta over here. And what would be horizontal component? Let's first see vertical. Vertical component of this tension is clearly T cosine theta. But because we have this approximation, and we take now this approximation to be true, then this is equal just T, because this one is 1. Now, how about horizontal component of tension? Well, clearly it would be T sine theta. Except that here we have to put minus. Now, why would we have to put minus? Notice that horizontal component of tension acts in the opposite direction of positive R. I displace this over here, tension tries to put it back. If I displace this over here, R goes in this direction, horizontal component of the tension acts in the opposite direction. You can also, that's one way to explain it. Another way to explain it is that notice the relationship between tension and theta. Theta over here is positive, it's counterclockwise. Tension is in the opposite direction. So there is opposite relationship between horizontal component of the tension and theta. If I go to this side, then tension is acting in this direction, but theta is in the clockwise direction, which is negative for an angle. And again, we have this negative relationship between horizontal component of the tension force and theta. At any rate, if we now take this approximation for granted, then this is equal to negative t times theta. But what is theta? From a radian measure of an angle, theta is r over L. And I put vector r because it depends how I displace it. Namely, r has component in the x direction, has component in the y direction. Okay? And L is clearly the length of this pendulum that I said over here is L. Okay? So horizontal component of tension will of course have component in the x direction, so that will be negative x theta over L, and negative xt over L, and in the y direction it will be negative y theta over L. But I will write that down soon. So now, when I decomposed tension, let's go further and write second Newton's law for this ball over here. So we say that mass of this ball times acceleration is the sum of all forces, second Newton's law. And the forces, I listed them, are mg plus tension plus, let's just write Coriolis force for now, plus Coriolis force. Now, mass times acceleration is further equal mg plus tension, and Coriolis force is negative 2m omega angular velocity of the Earth cross velocity of this velocity of the pendulum, of the ball at the end of the pendulum. So now we need to find this. And let's do it. Well, so omega cross v is equal, I will use determinant to find this. So this will be unit vectors I, j, k. Components of omega, we know from my previous videos, I derived that at least 5 to 10 times. So components of omega in the I direction is 0, in the j direction is omega cosine phi, where phi is latitude, and this omega without vector is intensity of this angular velocity, and here is omega sine phi. And components of velocity, and now I will write this as the second derivative of displacement. So it will be x dot y dot and 0. Namely, you will agree, if the displacement angle is very, very small, then the component of velocity in the z direction, in the vertical direction, is so negligible that we just neglect it. So we neglect w, and that's extremely good approximation. For those of you that don't know what is x dot, so that's basically dx dt, okay? And dx dt is u component. Because we will now have a lot of differentiation, it's easier to use dot than carry these d dt's. So this is further equal in the I direction, we will have 0 minus y dot omega sine phi minus in the j direction I will have 0 minus x dot omega sine phi, and maybe I can squeeze it here, plus in the k direction I will have 0. I will have 0 minus x dot omega cosine phi. Okay? So this is further equal negative y dot omega sine phi in the I direction. Minus and minus will give me plus x dot omega sine phi in the j direction. And here I will have negative x dot omega cosine phi in the k direction. Okay? Or this whole force will be, so negative 2m omega cross v will be, so this negative and this negative will give me positive, and let me immediately write Coriolis parameter f. Coriolis parameter f is 2 omega sine phi. We introduced this million times, and there is also f prime that is 2 omega cosine phi. You can think of these as substitutions or go back to my previous videos and see physical meaning of these. So with these substitutions, this equation, when multiplied with negative 2m, will become this negative and this negative will give me positive, and I will have this mass m omega 2 sine phi, so that will be f times y dot in the I direction. Here I will have minus because of this minus, so I will have minus m f x dot in the j direction, and this minus and that minus over there will give me plus in the k direction m f prime, because of cosine, x dot. Okay? So this is Coriolis. What did we do now? We have, just to recap, we have 3 components of the Coriolis force. We have 3 components of the tension in the vertical direction, and here 2 components of the tension in the horizontal direction due to this R having x and y components. And we know that G is just negative G acting in the vertical direction. So we can write this vector equation as 3 scalar equations. And then we need to solve that system of equations. And now I need to erase this, and then we will rewrite this as scalar equations and then solve them. Okay, now I erased blackboard. The equation that was here, let's write it as three scalar equations. In the x direction, and x in atmospheric sciences is zonal direction, west to east, positive eastward, we have that the mass of the pendulum times acceleration in the x direction, and I will write acceleration as the second derivative of the displacement, x2 dots, is equal, since there is no gravity in the x direction, we have tension, and that was negative tension times x over L. I derived that somewhere here and erased it. You can go back and check. And we have plus m f y dot. In the y direction, which is meridional direction from south to north, positive northward, we have m y2 dots is equal negative t y over L minus m f x dot. And in the vertical direction, z, where positive z is up, we have m z2 dots is equal. So we have gravity, which is negative mg. We have tension T. All this is now derived in the erased part of the blackboard. And we had acceleration due to, or rather Coriolis force in the vertical direction, mf prime x dot. Now, this is a system of equation. You can start solving, but you will not get far away without introducing certain assumptions. And these assumptions that we will introduce are very, very reasonable. Let's put it here. If we have this pendulum that is displaced for small angle theta, we already said that it will swing back and forth like so. And we already said previously that vertical component of velocity is negligible. Therefore, acceleration in the vertical direction is also negligible. We are assuming that oscillations are entirely in the horizontal plane, and that is excellent approximation if theta is very small. So now you can see why it is important not to displace this a lot, because then theta will not be small and you cannot make this approximation. With this approximation and acceleration on the left side being 0, that means these three forces have to add up to 0, and vertical component of Coriolis force is extremely, extremely small compared to gravity, which means that gravity is only balanced by tension. And this is extremely good approximation. If you just look at this logically, if this is oscillating in horizontal direction, horizontal plane, tension of the string is the only significant force, neglecting air resistance or anything like that, that is balancing mg. So, vertical component of Coriolis force is really, really small and negligible, and we also saw that from previous videos when I was calculating vertical component of Coriolis force, Eltwos effect, namely. So, from this equation, notice that tension is equal mg after we accept these extremely good approximations. Knowing this, we can go now to these two equations and replace t over here to get m x2 dots is equal negative t is mg, mg over L times x, and plus m f y dot, and the second equation becomes m y2 dots is equal negative mg over L. Of course, L is the length of this pendulum, y minus mfx dot. Now notice that very conveniently, all masses cancel. So at the end of the day, it's not even important what is the mass of the pendulum if you accept these approximations that we introduced throughout the video. And now I can rewrite this as x, 2 dots is equal negative g over L x plus f y dot, and y 2 dots is equal negative g over L y negative f x dot. And this is the system of equations that we need to solve. As I said at the beginning of the video, this is a relatively nasty system of equations. But we love nasty equations on this channel. Relatively nasty because these are coupled equations, and they are coupled through these f terms. You can see that here x dot appears in the y equation, but at the same time we have second derivative of x as well as x in the x equation. And the opposite happens for the y in the x and y equations. So very nice revelation from these equations is that if Earth is not rotating, if Earth was not rotating, f is 0. If f is 0, notice that these equations decouple. Wouldn't that be nice? But Earth is rotating and these equations are coupled. And this derivation, I hope, also shows you the beautiful, beautiful interplay between mathematics and natural sciences. If you introduce reasonable physical approximations and you know what you are doing, mathematics is leading you through the problem, through the derivation. And that's why we say that mathematics is the language of nature, language of the universe. That being said, how do we solve this system of equations? Well, smarter people before me figured out how to do it, and I follow their lead. To solve this system of equations, you multiply second equation by I, knowing that I is square root of -1, namely imaginary unit, and then you add this equation to this equation. Generally, how to solve a system of differential equations or a single differential equation, it's a trial and error. People before us tried different things, and some of these things worked, and they were kind enough to tell us how to do it. And that's how we know how to solve, for example, this system of equations. So you multiply by I, you add to this equation. If I do that, I will get here x 2 dots plus I y 2 dots is equal what? Is equal negative g over L. I factor out g over L, and I will get here x plus I y, and for these terms I will say, let me think now, plus f, and then I will get y dot minus I x dot. Now I will introduce a substitution that zeta 2 dots is equal x 2 dots plus I y 2 dots. With this substitution, I go here and I get that zeta 2 dots is equal negative g over L times zeta and negative I f zeta. Now, some of you might say, whoa, how did you get this one from this? because here you have x plus iy, x plus iy, so it makes sense. But how did you get this one? Well, I'll explain you how. Let's see what this term is. Negative I f zeta. Zeta dot. Negative I f zeta dot would be negative I f zeta dot will be x dot plus I y dot. You agree with me? And this is further equal. This times this will be negative I f x dot, and here I will have negative I squared fy when I multiply this and this. And this is further going to give me negative if x dot square root of I squared is negative 1, and this negative will give me positive fy. And notice that this is equal, if I factor out f, that this will be equal y minus y dot minus ix dot. And I hope that you will agree with me that this over here is exactly the same as this over here, and therefore you can see that this is indeed equal to this. So now you can see from all this derivation that we get that zeta 2 dots plus I f zeta dot plus g over L zeta is equal to 0. So now, using these smart manipulations, we reduced system of two equations to one second order differential equation that is homogeneous, but it has complex coefficients. How do we solve differential equation that has complex coefficients? Usually, you are given equation where you don't have I when you are dealing with differential equations, and you do blah, 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 and you solve. But now, if you stick with me, you will learn how to solve second order differential equation when you have complex coefficient. Let's erase again blackboard and do that. So our equation was zeta 2 dots plus if zeta 1 dot plus g over L zeta is equal to 0. How do we solve this? Because we have complex coefficients. Well, it turns out you solve it the same way you would solve it if this is not complex coefficient. Namely, we seek for a solution zeta is e to some k t, and k is some number, and t is time, because these are derivatives with respect to time. If they were derivatives with respect to x or y, then you would have x or y over here. Now, if you differentiate this twice, plug in here, once plug in here, you will get characteristic equation for this differential equation that says k squared plus if k plus g over L equals 0. Or k1 over 1, 2 is equal negative if plus minus square root this squared but I squared is -1, so this will be -f squared minus 4 times this g times 4 divided by L. Sorry, this is g times 4 divided by L, and everything divided by 2. So now what I will do here is I will plug these 2 into the square root. It will be convenient. So I will get that k1 over 2 is equal negative if over 2 plus minus square root of negative f squared over 4 and negative g over L, because this 2 will become 4 and cancel with this 4. Or k1 over 2 is equal negative if over 2 plus minus. Notice that I can factor out -1, and this will become f squared over 4 plus this. And this -1, when I take square root, will become I square root f squared over 4 minus g over L. And I am getting out of the chalk. Now, another assumption that we will introduce here, which is very reasonable assumption, is that this term, sorry, this is plus here because I took I minus, that this term is much, much smaller than this term. Let me show you why. So what we are saying is f squared is much, much smaller than g over L. And then f squared over 4, this 4 doesn't matter. What is the order of f? Order of f is 10 to power negative 4. We know that from my previous videos. And order g is approximately 9.8, 10 meters per second squared, and L is approximately, we said 60, 70, 80 meters, so let's say 100 meters. So this becomes order 10 over 100, that's 10 to power negative 1. Look how smaller this is. And when I square this one, it will become really, really small. So I can safely neglect this term compared to this term over here, and I get that k1, 2 is equal minus I f over 2 plus minus I square root g over L. And now k1 is equal, let me factor out I, so I will get here I minus f over 2 plus square root g over L. And k2 will be I minus f over 2 minus square root g over L. Now, you have to know from mathematics, because this is a linear differential equation. If this is solution to this differential equation, and I have 2k's over here, then a linear combination of any of these two solutions will also be solution. Namely, what I'm saying, that zeta equals some arbitrary coefficient C1 e to k1 t plus some arbitrary coefficient C2 e to k2 t is also a solution of this differential equation. If this is solution of this, then this is also a solution of this, because this is a linear combination of two solutions that are itself solution, and that because the equation is linear, this is satisfied. Where C1 and C2 in principle can be complex coefficients. Now, because this is solution of this equation regardless of C1 or C2. You can choose any numbers over here and the solution will be satisfied. Because I can choose C1 and C2 to be whatever I want, I will choose them conveniently for my problem that C1 is equal C2 and that is C over 2. So they are the same and equal some new constant C over 2. Now you are asking yourself, why C over 2? This is convenience, and you will see how this 2 will nicely cancel with another 2 that will soon appear in our derivation. And again, my support is I can choose whatever I want, so I will choose this because it's convenient. So that being said, let's now plug in these solutions over here and rearrange this. So zeta is equal C1, and C1 is C over 2, E K1 is this. So that will be I minus F over 2 plus square root G over L times T and plus C over 2 E to I negative F over 2 minus square root G over L times T. Now I will use basic trigonometric identity that E to I times alpha, some arbitrary alpha, is equal cosine alpha plus I sine alpha. And you have to know from trigonometry, from mathematics, if you have minus over here, then this becomes minus over here. So with plus you have plus, with minus you have minus. This is in famous Euler formula in mathematics, you should know that. So with that formula, I can rewrite this, noting that zeta is equal C over 2. Now notice that E to negative IF over 2 appears in both of these. So I will factor that out. E to negative IF over 2 times T. I factor that out, and then I would have E to I square root G over L times T, and here I would have the same but with negative sign. And these I will rewrite using that formula over there to get cosine square root G over L times T plus I sine square root G over L times T. That is this term over here. And now this term over here will be plus cosine square root G over L times T minus, because of this minus, I sine square root G over L times T. Now I hope you are not Bacon and you can immediately see that this one and this one nicely cancels. And look, this plus this will give me 2 cosine, and 2 cosine, that 2 will cancel with this 2. That's why I picked conveniently that coefficient C over 2. So I will get that zeta is equal C E to negative I F over 2 times T times cosine square root G over L times T. Or finally we can deliver the final blow and recognize that zeta is x plus iy, that is the substitution that we introduced, is equal c, this one I again rewrite using that formula over there. So I will get cosine f over 2 times t minus I sine f over 2 times t times this cosine square root g over L times t. And now let me write the final solution here. So what we need to do is, look, we group together real part to real part, imaginary part to imaginary part, and these are our solutions. Hey, look, x as a function of time is equal some constant c cosine f over 2 times t cosine square root g over L times t. And y as a function of time is equal negative c, some arbitrary real constant, sine f over 2 times t times cosine square root g over L times t. And if this does not deserve one beautiful box in green, gray, as well as red, then I don't know what it does. This is absolutely beautiful solution that we got after, well, I don't know how this video is long, but very long. This is motion in the x and y direction of our pendulum. Let's remind ourselves, what did we do here late in the evening? So we had pendulum, this is equilibrium, this is positive z. Pendulum is displaced from the equilibrium for some small angle theta. Length of the pendulum is L, gravity is acting down G, F is Coriolis parameter, F is 2 omega sine phi, omega is angular velocity of the Earth, and phi is latitude. And now this pendulum swings back and forth, back and forth. If L is very large, long, theta is very small, and we carefully design this experiment, this will be the motion of the pendulum in the x and y planes, where x, I said, is like this, and y is into the blackboard. Notice that the frequency of the pendulum will be the same as the frequency of regular pendulum. But there will be redistribution of motion from x to y direction and vice versa. Exactly what I told you. After a few hours of derivation, I'm even more excited now. So, if this is that pendulum and I swing it, due to Earth's rotation, let's say I swing it like this in the x direction. In the x direction, after some time, this cosine f over 2 times t will move this motion into y direction, like so. And then this sine, negative sine f over 2t will again reverse this motion into the x direction, and pendulum will make beautiful flower-like pattern. So you can see something else that is extremely beautiful over here. Let me put this back. I'll put it back later. Another beautiful thing that you can see here is the following, that these terms do not damp down oscillations. So if the displacement was like this, and we assume there is no friction due to the air, the amplitude will never change. The amplitude will never change. We will only have change of motion from the x to y back to the x direction, but the amplitude will always stay the same, always the same. And now, well, I could stop this video here, but I will blow your mind for the last time in this video so that you can see the beauty of mathematics and physics. What you will see now is incredible. What you will see now is this. This is equation that we solved to get this motion. Zeta 2 dots plus I f zeta dot plus g over L equals 0. You are not impressed, but look at this. If you have this equation, zeta 2 dots plus f zeta dot plus g over L equals 0. Namely, if you have the same equation but you remove imaginary unit, you will have damped oscillations. If you are an engineer, you should if you are an engineer and you don't recognize this equation, you're probably not so good engineer. In engineering, this f is not Coriolis parameter and so and so. Look at the general how the equation looks like. They look absolutely the same in terms of form. The only difference is imaginary unit. If we have imaginary unit, you get these terms that kind of damp oscillation, but without damping amplitude. They damp oscillation by removing oscillation from x and moving it into y direction, but without changing amplitudes. But if you have a spring, or you have this one, and the air friction is affecting it, you will have damping, and that damping will look like that without this I. So you can see that two equations that look almost the same have completely different applications or implications. In this case, there is no damping, and that's because of this I. Motion is just redistributed. in this case you have damping and eventually the motion will die out. So next time when you brag to your professors about imaginary numbers, oh, do I have to study I, complex numbers, you can see how big of a difference it makes. And that's just like in real life. Two phrases that look very similar or sound very similar can be completely different. End over and bend over. Very similar, but completely different meaning. Very similar, completely different results. If you stayed with me until the end of this video, thank you very much. Until next video, goodbye.